Good afternoon to everyone who's just joining us. Thank you for joining us. We have just over 5 minutes before we'll get started, so just hold on and we'll make a start at the hour. Good afternoon and thank you for joining us for today's event. We'll be starting in about 4 minutes. We're just seeing the numbers gradually go up. So please bear with us. We'll begin on the hour. Thank you for joining us for today's event, where we're going to see the numbers of participants are still going up. I expect we'll start in 1 or 2 minutes, so just bear with us. Thank you. Thanks again for everyone who's joining us today at the event. I can still see the number of participants going upwards, so we'll give it another perhaps 30 seconds to a minute before we get started. Okay, it's just past the hour, so I think we'll make a start today. Thank you very much for joining us today on what is the latest in the series of collaborations in webinars between CBSE and the ARM School Programme, really centered around the topics of physical computing and project-based learning. Today's session is around play-to projects, looking at the transition from typically young learners as they move from primary school to secondary school, from play to project-based learning. Before we get started, I would like to thank CBSE, to thank Dr. Saha and Mr. R.P. Singh, and to welcome Mr. R.P. Singh to today's event. It's been a real pleasure to present the sessions up till now, and we're now in the middle of the series, and we have 3 more to go over the coming months. As part of this presentation, we'll just do a summary shortly of our sessions so far, and I'll explain where you can access those recordings later. Okay, let's move on. So starting with this welcome and introduction, I will give a little bit of background on the ARM School Programme. We've done this in previous sessions, but I think it's worth giving some context to teachers who may not have joined previous sessions. We'll then go on to the main professional development session, which is going to be run by my colleague, Rob Lehman. I'll then hand over to Surya, my colleague, to talk about feedback on the session. We always really welcome teachers' thoughts and feedback on what worked and what they would like to see in future sessions, which we then take on board for future presentations. We'll then do a Q&A of about 15 to 20 minutes and finish the session. I expect that the full session will last in the region of an hour and a half in total. Okay, so before we get started, I'd just like to mention a couple of housekeeping points. Firstly, if you have any questions throughout the session, please do put them in the Q&A, and my colleague Surya will endeavour to answer them as we go along. If there are any questions that come up through the professional development session, then we will gather those up and answer them in the Q&A at the end. So yeah, we'd really welcome any thoughts, any questions that you have about the topics we're presenting on today. And also to mention on certification. So a common question that comes up in all of the sessions is where do we get the certificates from for attending the session? Certificates will be emailed out to you after the session, along with a link to the recording of the event. So that's where you get your certificates. Okay. So just a brief introduction to your speakers. My name's Nick Sample. I manage the ARM School program. My background is really in education and educational publishing. So I've worked across a number of different countries, principally in STEM publishing for schools from across the UK, the Middle East and the US, before then, about 4 or 5 years ago, joining ARM to set up the ARM School program. And the main session will be run by my colleague Rob. Rob is a computer science teacher. So he has worked in teaching for about 10 years before then moving into curriculum development. So he worked with exam boards over in the UK, setting the specifications for exams in the UK and internationally. So you're very much in good hands when it comes to the professional development session. Okay. So let me tell you a little bit about the school program. As you may know, ARM is the sort of basis for ARM is really around semiconductor design. So we create essentially the blueprints for the microprocessors that you will find in lots of devices, lots of connected devices, from laptops to mobile phones to even household devices like fridges. But ARM doesn't actually manufacture anything. We create the blueprints, the plans in a sense, which we then license out to organizations that then manufacture the chips. So as part of our role really at the start of an ecosystem of technology organizations, we feel it's really important that we take a stake in schools education and really work with that network of organizations that we work with to help support teaching of STEM education in the classroom globally. So our vision as a program is to empower all learners with the opportunity to develop the interests, knowledge and skills that enable a lifetime of engagement in STEM. And that's whether the learner goes on to work within the technology industry, work within science, or simply as an informed citizen who can make choices, the right choices for them around things like use of data, this sort of thing. So the school program, as I mentioned, was set up 4 or 5 years ago, and our way of working really is to support teachers in the classroom. So we work with teaching organizations, communities of practice, to support the evolving sense of what is best practice within STEM and computing. Our real sort of center of gravity really is in computer science, but as we'll look at in the professional development session, a lot of the ideas that are presented within a very practical approach to the use of computing in the classroom really do apply to multiple subject areas, most notably the STEM subjects, but also going into topics like literacy. So you know, it's a very, very rich ground to explore. To support teachers in doing this, we have a professional development program on edX, which is free to access. All of our content is free to access. So you can find that on edX.org if you search for project-based learning. We also have on our website a range of free to access materials that you can download, and I've put a link there to our site. And here it is. So this is what it looks like. And at the top of the page, I'd really point you towards this. There is a link to a brochure which you can download, and it really does walk you through end to end the ARM School program, our approach, and the support that we offer teachers. And this is what that brochure looks like. So I would very much recommend downloading that and taking a look if you're curious about the what else we can do for you as teachers. And you can also on our site you'll find a box at the bottom of the page where you can enter your email address and subscribe to our newsletter, which comes once a term, so once every few months, and it just gives you a summary of the updates from our program. And the professional development program that I mentioned a minute ago on edX.org is broken into 3 courses, as you can see here. And the as I mentioned, it is free to access, and the webinar series that this session forms part of really draws upon the themes that are covered across those three and 4 courses. So if you're curious at all about exploring any of the topics that are raised throughout the webinar series, we'd really encourage you to sign up to the edX program and try out one of the courses. It's free to access. Each one takes in the region of 10 to 12 hours to complete if you include the classroom practice as part of it. If you just go through the material, it's probably a few hours, but it does take a deeper dive into the topics that we're discussing. Now this session, which is highlighted here, is pretty much in the middle of the series that we're running with in partnership with CBSE. If you would like to access previous sessions, you'll find links to those on the community site where you registered for this event. So that's the ARM community site. Future events. So the next one coming up is we've got in February and then March and April. Next one is on assessing projects in physical computing. So one of the issues that a lot of teachers have with physical computing and project-based learning is how to effectively assess it. So it feels like a very, very different way of managing a classroom, a very different way of facilitating learning compared to a more didactic approach. So assessment is something that is often a concern for teachers before they embark on trying project-based learning out. We're going to present on that and just walk through some methodologies that you can use to assess your students' progress in carrying out their project-based learning activities. We'll then go on to look at the affordances of project-based learning of physical computing for developing employability skills. And these are the sort of skills that employees would use in companies like ARM, whether they're engineers, whether they work in more on the corporate side of the business. Skills like resilience, attributes like resilience, skills like teamwork, communication, this sort of thing. So that's going to be the next session. And then we finish with how to run an innovation day. An innovation day is a fantastic way of engaging your students with technology. It can be run in about 5 hours with either a class or a school or multiple schools, as we've done previously on the school program. We've had teams from up to 25 to 30 schools come together to compete on an innovation day, competing to build a solution to a problem connected to the global goals. So this is something that we'll talk you through. If you want to run your own innovation day, it's relatively straightforward. There are a few tips that are useful to know, and we'll close the webinar series by covering that, and hopefully that's something that you can take away and run with your school in the near future. Okay, so we now enter the main training session. So I'll hand over to my colleague Rob Lehman. The training will last about an hour, and then we'll come back to, I'll hand over to my colleague Surya to talk about feedback, and then we'll move into Q&A. Okay, thanks. Over to Rob.
Hello and welcome to the latest ArmScore program session in collaboration with CBSE, all around from play to projects. In today's session, we're going to be looking at some simpler versions of project-based learning and how that reflects in the practice of play-based learning, which is very, very similar to project-based learning, but just differentiated and scaffolded slightly different for younger learners. We're going to look at how to understand the ASP schema and how to apply that in a simpler setting for younger learners, and understand the differences between project-based learning and play-based learning. We're going to be looking at several different examples of projects which we can apply through physical computing and play-based learning, and understand how to support learners in getting the most out of these when teaching computing. We're also going to be looking at some of the physical and hardware considerations around these sorts of projects and how to simplify these things to make their delivery with younger learners more effective. And we're also going to be looking at the types of context that we can use for the types of projects and how to actively engage learners. So we'll start off with a really nice quote from Piaget, which really sums up why we use project-based learning and play-based learning. And it just really captures the sort of the nuance of why we do this, and what is the goal of education, and is it just about structuring the learning around rote teaching and learning, or is it more about trying to develop creative and innovative minds? And I think this really kind of underpins everything that the ArmScore program's resources and approach tries to push towards. It's this trying to teach learners how to think and apply technology creatively to make new discoveries and to learn more effectively. So, what is play-based learning? We've looked at in previous sessions what project-based learning is and dived into the nuts and bolts of what makes up project-based learning and how the ArmScore program defines what that pedagogical approach is. Now, play-based learning is very, very similar. It's slightly simpler, and it's nuanced and simplified so that it's much more easily applicable by teachers for younger learners. And that has a dual approach insofar as that younger learners obviously less experienced with technology and computing and all of the subjects that we're trying to instill upon them, and also generally teachers are less specialist around the sorts of technologies that we seek to apply. But what is play-based learning in its simplest form? So play is a defining feature of human development. We all play as children. This is how we learn, and play is inherently engaging. Children will naturally play, and you see this throughout humans and also animals, that play is how we learn to cope and deal with the real world. And this inherent engagement of play can be harnessed by educators to enhance learning and to make it more effective. It's essentially adding scaffolding or a structure around play to focus the play to be more useful in what we're trying to get them to do or to learn learn about a particular subject or a particular context. So it's a really, really useful way of getting the natural engagement of play and harnessing it and applying it to teaching a particular subject or context. And we'll see various examples of that as we go through today's session. In the classical sense of play-based learning, it's child initiated and teacher supported. So you would, or certainly in the literature, children are let loose and sort of learn by doing, and then the teacher will support them by asking questions with a slightly sort of Socratic approach about, why are you doing this? Have you thought about doing X? What is the consequence of doing Y? Almost, and you can think of it almost a bit like some of the elements of the Prim approach as applied in computing, where you're not directively structuring the session with the learner. They are still playing, but you're just sort of poking them in the right sort of direction by posing interesting questions and try to lead in learning in that way. Now, in the ArmScore program approach, we sort of structure it slightly more than that. I think this is a a feature of project-based learning as well is that we're adding more construct around the learning experience to try and shape it more vigorously, I suppose, and that makes it more effective, really. But then that also means that teachers have to be experienced with how to apply to make it more effectively. But ultimately, play-based learning is all about learning through doing. It's about getting that motivation to play, stimulating the learner, and enhancing that experience so that they develop new skills. And in so doing, especially with group work, they're developing communication skills, language acquisition, collaboration, and just generally concentrating more on their learning. So there's a lot to be said for play-based learning and how this eventually develops into project-based learning as they progress through their time in school and through the various curricula that they're learning through this pedagogical approach. So why is play important? Now, this is a really nice diagram that sort of sums up the 6 elements of play and how it can be used to teach or teach STEM subjects more dynamically. So it's a really, really important way to engage and motivate students. And you can see here, for example, I think a good starting point for this is the active nature of it and also the engaging nature of it. Now, it's easy to make projects and play-based learning not engaging and not active, so it's really important to consider how do you make your projects and your play relevant to what you're trying to teach them, but also fun and engaging and also ultimately meaningful. How do we keep that sense of joy for the learners whilst having that structure around ensuring that they're learning what we want them to learn? And there's lots and lots of different ways to do this, and by instilling a little bit more structure around what we're trying to get them to do in terms of the ARMSCORE program approach, with success criteria and using some hardware, we can retain all of the joyful and active and engaging elements whilst also having a solid foundation and a solid learning experience for the learners, and so they can progress through and actually learn things by applying the very skills that we seek for them to learn, and ensuring that it's meaningful. Again, this is all about context, which we touched upon and covered in depth in the last session, but why contexts have to be there to make the learning meaningful, and then also the delivery of it. The learning has to be iterative, and this is a good part of physical computing more generally, is the projects, because they have a physical nature to them, and you're programming them, and you have success criteria which builds in complexity. They have to iterate through that solution to improve it and to meet all of the success criteria. So all of these elements together and through the group work and making it socially interactive, it's a really, really powerful approach. There is some research showing that that play-based learning is up to 20 times more impactful than traditional didactic learning. These are quite small studies, as you generally get in educational research, but I think that's a really interesting statistic, that this style of learning is very, very, very impactful compared to traditional approaches, which I think is a testament to why we should be doing more of this, despite some of the logistical complications that you can get with physical computing and project and play-based learning more generally. So what is play-based learning and how does it interact with practical computing? Now, we've seen this diagram before. This is the ARMSCORE program schema. So this is all of the different elements that we need to consider when putting together project and play-based learning, practical computing learning experiences. So there is this element of hardware, such as like the microbit, Arduino, Raspberry Pi, etc. They need to, well, they don't need to, but it's good to have a sort of a basic understanding of the different electronic components. But for very, very young learners, which is what we'll be focusing on today, we'll be looking at just single pieces of kit. So, for example, microbits, and how we don't really need to focus on some of the more complex elements of the electronics and just use the device as it is, and try to eke out learning from that. An important element though is the input process output bit, so the IPO bit. That's a really important bit to understand. So we start to develop learners in their understanding of systems and how the input, how these devices take input and do something with it and produce an output. And there's always this making element as well, which this is really sparks the sort of the joy in learners. They have to make something. They're creating an artifact and they're applying computational practice to develop a solution or a product, which is all part of the the narrative and the context which we give them. And this all sounds a little bit esoteric, but we'll show solid examples of this as we go through today's session. And the next strand, so the bits in green there, we seek to give them problems which they can play to solve, and so these are relatively open-ended, although there is some concrete things that we want them to accomplish as they're doing it, but they do it through play, and these outcomes are linked to the curriculum. So the problems, whilst seemingly can be abstract, they do link to particular areas across different subjects, and it is cross-curricular, as we'll see in the examples. And we try to design them to be as engaging as possible. And some of the examples we've got today are quite bite-sized, so it's the sort of thing that may take 20 minutes, to an hour with younger learners, but these can be built upon and mixed together to create a much more chunky experience, and you could have this taking a full hour, a full lesson, or a full week if you wanted to, depending on how far you wanted to apply this pedagogy in your everyday practice. But ultimately, it revolves around letting the students play with the problem set, with the hardware that we give them, and solving real problems. Now, with all practical computing projects, there is an element of programming in this, and so whilst this might seem only applicable to computer science, you can use these physical devices to teach cross-curricularly and apply programming to do or to eke out learning from other subjects, which again we'll see examples of as we go through, and learning the sort of the basics of the computational constructs and applying them confidently is really, really important, especially with in terms of practical computing, and these can be used to solve problems and demonstrate theory and principles in other subjects, again, which we'll look at. And the last bit is this concept of design and creativity, because we're creating physical assets or creating physical artifacts. We should encourage learners to design what they're going to do, so this sort of helps them think about what they're trying to achieve before they're actually doing it, and they can do that creatively, which again has that sort of joyful element to it, because they can apply their creative skills and create something which is meaningful and it's theirs, they own it, they made it, but at the same time they have thought about the problem set that they're trying to solve. And ideally we want them to do this collaboratively, we want them to do this in groups so that they can enhance all of Fulham's 6 C's, communication, collaboration, etc., which we'll touch on shortly. And so this is, again, enhances that learning experience by working in groups collaboratively to solve problems in a meaningful way. And this entire approach is exemplified in all of the ARMSCORE program's resources, which you can get for free online, and there'll be links to this later on. So just to refresh ourselves on what the ASP schema is, because it's really important to understand this structure and how this is applied through the projects that we're going to go through. And this really is what you can use as a template or scaffolding to allow you to create your own play-based learning activities or project-based learning activities, depending on the age group that you're working with. And so whilst it's relatively straightforward in applying, the structure of this is really, really important. So let's just go through it in order. So first of all, we give the learners a context or a scenario, and this is the sort of the hook which gets learners in. So this is what makes it relevant and engaging for them. It's useful if it is familiar and relatable, so it's something that students will already have some understanding of. And with young learners, it's really important to have a set, well, your learners better than anybody, so it's really important you can give them a context or a narrative which is something that they can relate to, and that could be something in the local culture, in the local ecosystem, something in the school. It could be a theme which the school is celebrating. It could be a local religious practice or anything really. You can base these projects on almost anything, as long as the learners start out with some familiarity with it, or it has that sort of human link, and it's something that the students will sort of generally understand the conception of. And once you have that context and that narrative, you can then bake in some more of the formal structure around the success criteria. So this is the learning objectives. This is what we want them to actually do. And this is where we sort of take a slight step away from traditional play-based learning, where it's you just give them something and let them play with it. And it's that sort of classical constructivist and constructionist approach where it's just sort of learning through osmosis. And we try to bolt on some structure to ensure that there is something relevant and that the play is leading them towards understanding of a concept or principle of which we are designing the activity to get them towards. So it's useful when crafting success criteria to start really simple. make it achievable, make it so they can do it in a matter of minutes, and be very, very specific as well. You make sure that when you're writing the success criteria, that the students can understand what it means, and you can craft these in very, very cleverly so that it seems quite simple, but when they dig into the solution to the success criteria, they have to apply, for example, computational techniques in order to do so, and we'll look at examples of this a little bit later on as well, and that way you can eke out some of the complexity in this, and that's really where the learning happens. So they understand in principle what they need to do, but to do that they have to apply computational skill, and I think that's the sweet spot in project and play-based learning more generally, is sort of almost masking the complexity of the learning in the task that you're getting them to do, and they're enjoying doing it whilst they're on that journey. So the next bit is the pro tips. Now this is a little bit more malleable. It's you can apply these liberally or not at all, depending on your learners and whether they need support or not. And this is part of the practice of play and project-based learning. It's intervening where necessary. It's only give the students support when they need it. And that's really when they are stuck or they become disengaged. And really, you don't want that to happen at all. So you have to be quite on the ball with how you support your learners. And you can do that through various different ways. It could just be asking them questions. It could just be giving them support material. It might be partial solutions. There's lots of ways to do this, and when we look at the examples later, I'll show you some examples of partial solutions, and you could even break those down further and only give them partial solutions, so you can just prompt them and prod them into the right direction. Next bit is stretch tasks. So this is essentially additional success criteria, and this is there to stretch your more able learners. Most classes are mixed ability, and some students are going to get through the success criteria quicker than others, and so it's really important to have some additional goals there that can make these tasks more complicated and also more open-ended to keep these learners on track, and they can just improve their product and make sure that it meets the success criteria more thoroughly without going off piste and doing something completely differently. So getting successful or good stretch tasks is really, really important to keep the learners engaged and on topic. And then at the very end of the lesson is this sort of final thoughts, or this reflective exercise to consolidate the learning, to get them to think about why they are doing or have done what they have done. Has their artifact, has their solution met the success criteria, and why does that matter? And that's sort of like closing the circle of this, and making it all concrete and absolute once again, so that they understand what they've done first of all, and the sort of profundity of that, and also what techniques they've learned, because they may have learned new computational techniques whilst going through some of these problems and not even be aware of it. And that's the sort of the magic of this approach, is that they are doing complex things almost hidden amongst the activities. So having an understanding of this schema is important, because this is reflected in all of the tasks that we publish as part of the ARMSCORE program, and you can use this again as a framework to create your own teaching and learning activities as part of project or play-based learning. So there's a couple of other pedagogical tools which are useful for this. Now these are the same as in project-based learning, and again these are there depending on what age range you apply this to, because you can use play-based learning with very young students, but also up to older students, up to sort of grades 9 and beyond. But an interesting model to use and to get students to think about is this IPO model, so input, process, and output. And this is particularly useful for STEM subjects, and even more particularly useful for computing-based projects where you have these physical devices that you are seeking learners to develop artifacts from. And so they have inputs, they have things like microphones, buttons, and the like, that those inputs can be then processed. So you can take, when a button is pressed, that can trigger a particular process and consequently trigger an output. So getting students to think systematically in this way is really, really important, and applying this as a problem-solving tool is really, really important. And we'll look at examples of this again with the projects that we come on to shortly. Another element of which really helps with STEM and just projects more generally is design thinking. Now you might think this sort of is separate to play, and that it kind of formalizes a little bit too much. And I would agree. This maybe makes it a little bit too formal, but this is here as a tool. And if you want to give students something slightly more formal, then getting them to design their projects is ultimately beneficial, because it makes them think harder about what they're doing. It helps them iterate on their designs. It makes them focus on the objectives. It makes them consider their users' needs, and they also get to design elements through drawing, to consider the materials that they've got when they have to make an artifact. And it helps them sort of prioritize which features they're going to develop first, and ultimately helps them analyze what problems they're actually solving and how they do it. And you can also tag on things like more multimedia elements like branding, logos, and that helps with the whole teamwork. It helps them sell their solution. It also makes them iterate and improve upon what they've developed. So this is a tool to be applied depending on your intuition with your students. Would this help engage and motivate them?
Hi all. Yeah, so that seems to be a technical issue. Please hold on for 3 minutes. We will resume it soon.
Is this a good starter activity, or would this switch them off in the first place? So play-based learning, this is something that can be applied with older students, not necessarily younger students, but it's just there in the quiver of PBL tools. Another really, really important element that we talked about before was this element of iterative development, and this is fundamental to physical computing activities, but also in any subject where we first of all get learners to focus on the success criteria. We want them to plan and design it, but that isn't completely necessary for play-based learning. We do want them to develop a solution, and they can sort of usually skip over the plan bit of it and just jump straight into solutioning, generally because the problems we give them for play-based learning are simpler and are sort of small chunks, and so they can just jump straight into iterative development, and then they test their solutions and then conduct obviously remedial action where that is necessary. And they'll probably go through this cycle many times. Usually with these smaller play-based activities, you'll only give them 1 to 3 problems, and so they'll only have to go through this a few times. But generally, if they've not used the tools or they've not applied the computational techniques required with these projects is that they'll go through this a few times, and it's useful to get them to get used to this. And this is where we can introduce this concept of fail early and fail often, and not allowing things not working or things going wrong to disengage students. And this is something that students need to develop, their sort of resiliency, really. And I've certainly experienced this in teaching, where if it doesn't work how they intended straight away, students can switch off and they don't know what to do. They become disempowered. And really, we need to condition the students so that they're confident in being iterative in their development and applying problem-solving skills to work out what went wrong. You know, is the input what we expected? Is it being processed in a logical way? Is the logic in their program doing what we think it does? Is it testing for what we think it does? And is the output sufficient for the input? And ultimately, does it solve the success criteria? And so this is where they need to evaluate their product, evaluate their solution, and see, is it doing what we want them to do? And I've certainly found this with students when you first introduce this methodology, is that they can get away from the success criteria and tend to go away and do whatever they like. And this is where, again, we try to steer the play, steer the what they're doing, so that it isn't just completely random, and that they are working towards coming up with a solution to the problem. And that, again, that's where that sort of slightly more formal approach of the ASP approach comes into play, and not quite so kind of open-ended, but that ultimately is beneficial for the learner. So I've mentioned Fullen's 6 C's before. This is a really, really important thing to consider when planning these types of activities. We want the students to conduct these projects and problems collaboratively. We want them to work with each other, and this helps motivate and engage the learners. And by doing these problems and these projects and through play, they are naturally working as a team. They're naturally collaborating. They are being collaboratively creative as well. They have to think about what they're doing, how they're going to solve the problem, and how do they ideate a solution based upon the resources that you give them. And you know, this is where some students may be stronger in certain areas than others, but by collaborating with each other and communicating effectively, they can all be brought along on that play-based journey. And so it's a really, really strong point of this. I mean, it's quite difficult to assess these soft skills, and you can generally only do it through sort of direct observation and having a schema that you can assess it through. And we'll touch on this in the next session based upon assessment of project-based learning. But you will see this naturally coming out as students work their way through the problem solving through the play in their group. So it's yes, it's an interesting facet which is happens naturally as part of play, especially in group-based play, and how that helps the group move towards the solution. So just to sort of summarize all this up, it's so the core elements to play-based learning. It's ultimately all about problem solving, and we want them to be solving a problem, and that problem can be contextualized, it could be subject-based, or it can be just something very, very simple. But how to get there, we want to encourage them to think in that input, process, output, the IPO model. We want them to work collaboratively, as we just mentioned. We need them to work iteratively, and being resilient as part of that. And it helps if they design it as well. So I would encourage everybody to consider this core sort of flower of play-based learning, and hold that in your mind as we're going through the different examples today, and how we can apply this in the real world and in the classroom. So just a brief talk about the hardware we're going to be looking at today. The example projects for play-based learning that we're going to go through have been designed to work with a Microbit version 2. There are obviously other development boards available as well, but these are all based upon this one because it has certain features which are really, really user-friendly, and it's a really good tool to use for play-based learning with younger learners because it's so accessible and easy to work with, and it just works. Other boards are available as well, but this has some interesting features. And just to draw your attention to the new features of the version 2, which is the latest one from the Microbit Foundation, is that the new Microbits have got a speaker on board, which previously they didn't. It's also got a microphone, so you can do more sound-based play. It's just generally faster. It's got a more powerful processor. It's got more memory available to it, and it also has an additional button. And you can see all the new features of that on the OMSchool program YouTube channel. So I won't dwell on this too much because this is for younger learners, but these devices can be just plugged in via USB and can be programmed via an online environment called MakeCode. So there are two ways to program the microbit for younger learners, and certainly with the play-based learning approach, we would expect you to use block-based an interface such as MakeCode. There are others available. There are many other ways of programming a microbit. There is the online MicroPython tool if you're working with slightly older learners and who may have already studied some computer science, but this does complicate it obviously, and I would advocate to stick with the block-based approach because you can do a lot more complex stuff with the blocks without getting lost in the syntax and the structure of the code, and it's just much more accessible and easy to work with, and you can do a lot more stuff faster with the blocks. But there are other tools available as well. It just makes connecting the microbit to the code much easier and quicker through this, because you just plug in the USB cable, hit download, and it just as long as you pair the device to the computer, it downloads the hex file straight to the microbit, and then you're good to go. And again, we need to just consider that process, make sure that learners are familiar with how to get code from the environment to the microbit, which takes just a few minutes. It's a relatively simple process, but just another part of this sort of physical computing approach. So let's jump straight into the example projects for the younger learners. So you'll notice this structure is based upon the ASP schema, and also similar to the examples that we went through in the previous project. These are just sort of simpler context with simpler success criteria, and we're focusing on the areas of the curriculum which are more applicable to younger learners. So the very first badge in this very first project is a name badge, and this is something that you could use as a project to get learners familiar with what a microbit is, or whatever device you're using, and get them to do something nice and simple. So the name badge, as you'd expect, we would want to have their student's name scrolling across the output or the LEDs on the badge that they're going to make. So thankfully the microbit has this LED matrix which they can look at, and they can obviously put their name in there using some relatively simple blocks. So the problem or the context is you're a new student in a school and you need to make a digital name badge so students or other learners can know who you are. So that's nice and simple, straightforward enough. And you might think, oh, that's a little bit too simple. But when we dig into the success criteria, we can add in some additional complexity should we wish to. So, for example, they have to create a digital badge using a microbit. So there's two elements there, because you'll obviously give them a microbit and the battery pack, as you can see there in the hardware, but they also have to consider how they're going to stick the badge to them. How do you actually make it into a badge? And so there is a making element to this, and this is where they crafting this into an artifact. So you have to consider how they're going to do it. They may wish to design it, or you may encourage them to design it. But that's just the first step, is how do you deal with the physicality of a name badge before you start worrying about programming anything. So there is that sort of making element, and you can use things like a small bit of card with a safety pin. You can maybe use Velcro tape. There's a number of different ways of doing it depending on what resources you have available to you. So that's just the first bit, and that's the sort of the art and craft and the sort of making element of it. So the next bit of it is to program the microbit to display your name, and this is relatively straightforward, and we'll look at an example of that shortly, but that is just getting them to think about how do you get their name to appear on the LEDs, and it's very simple, and it's very accessible, and most students will be able to work this out without your intervention whatsoever, and it's quite magical to see that happen, is when students can use a program like MakeCode or Scratch or similar, and just do stuff without even learning by doing effectively. To add in some additional complexity for this, we want them to add in an icon, and this is where the creativity comes into it as well, so that it shows their name and then the icon or a picture or whatever they decide to do. So this is where the play bit comes in as well. And then for a little bit more complexity, we want them to add a theme song when a button is pressed. So we're having some more of that input, which is the button press, and some output, which is a theme song. And they can use some of the pre-built patterns or music which are on the microbit, or they can design their own. And then the last one again is trying to make this joyful, is decorating the badge so they can express who they are. So they've got their name, they'll have an icon which represents them, and they're going to decorate the physical badge itself in an arts and crafty way to represent who they are. And this is where they can express themselves and, and be really creative. And this can be done as a group, or it can be done individually. This program works nicely as long as you've got enough microbits and resources to work with. So this is a nice introductory type of project. And with the sort of the showing them how to get the code onto the microbit, this might take half an hour to an hour depending on your class and what resources you have, and obviously what computers you've got available and the like. So this is a nice beginner friendly exercise and a really good place to start with younger learners. So let's look at the IPO table. Now, we don't want to dwell too long on this, but it's just getting the students to think about what the IPO process is. And you might wish to demonstrate this at first and then get them to use this as part of their design. But again, you don't need to, but it's a useful design structure to look at as part of the learning. And so the input initially would be, you wouldn't have an input for the name showing on there. You would just use some of the blocks, sort of the show string block, and it would be in a loop so that it would be continually showing. And then the output would be their name appearing on the LEDs, so kind of their name would scroll across the screen. And then we'd also have an icon after that, and also some melodies. But the melodies would involve an input because we want them to program it so that when they press a button, the melody or plays through the speaker. So you've got the input button process of triggering the sound, and then the output is the sound coming through the speakers. So very, very simple, and students will kind of get this just intuitively, but it's just getting them to think about that IPO process, which is quite helpful. So here is some example solutions for this. So this is about as simple as you can get with these sorts of programs. So you have a forever block, and obviously whatever sits inside that forever block runs forever. And then it shows us strings. This is where we're introducing some of the sort of computational constructs into this. So it shows you what their name is, and then it shows the icon. And they can even use make their own icons as well. There are blocks where they can just draw into those little darker blocks and make their own pictures. So that will naturally show their name and show the icons, and you can either lead them through this if they require that as part of the teaching, or you can let them explore and work it out for themselves. It's and then you intervene. Again, it really depends on how able the class is and how young they are and how much time you've got to dedicate to this. But you could do this as a lead exercise just for the first bit, and then let them work out how to do the rest of it. To get the sound to work with the V2s, you do have to have that on start block there where it sets the built-in speaker to on, so you have to turn the speaker on, and you'll see this in a couple of the other projects as well. So that's an important thing to not forget, because by default that isn't on because there are two versions of the microbit, and the V2 has the speaker whilst the V1 doesn't, so you need to enable that. And then more importantly, the bit underneath that is where you have the IPO model. So on button A pressed, so when the button A is pressed, it will then play that melody, and they can choose what melody that is. There are lots of pre-built ones, and they can choose how often it is played. So that's the computational bit there. And you can see the solution is relatively straightforward. You can use this, you could have this on the board, you could have this printed out on little bits of paper, or on card or whatever, and so you can use this to scaffold the learning and to show the learners how to do this. And so some of them will just get it intuitively, others may need a little bit more support, and this is the sorts of solution that you can provide to them. So hopefully that previous example made sense. Here's a slightly more complicated one. So for example, in this one, we're going to be looking at animation and concepts around sort of art and computing, timing, and what interaction is for this context. So the context is you're learning about animation, and we're going to create an animation of an animal that can be controlled by the user. So nice and simple. So you could tag this onto learning if you're looking at geography or biology, looking at habitats or anything like that. So this is where this cross-curricular element comes in, or you may look at it from the art and computing element and go, no, we're going to look at specifically what animation is, and how do we make animations. And this is quite a nice simple one because we just need the microbit and the battery pack for this. We don't need any additional hardware. So it's quite simple resource-wise. So the success criteria then is we want them to design and make an animation of an animal. And this is where the design bit could be quite helpful. So you could give them some squared paper, and they could design on that 5x5 matrix what that animal will look like. It could be, it could be almost anything. How do they represent an animal using a 5x5 matrix. And so there's a sort of a design there, and there's an abstraction layer where how do they turn a complex beast such as a lion or a giraffe or a dog into a 5x5 representation of that. So that's an interesting one. And then after that, we can then work out how to actually animate it. So there might be sort of a default state of the animal moving or doing something. It's useful to keep this to 2 frames, which we'll see an example of when we look at the solution in a minute. But they can animate it and make it as complex as they wish, and some students will really get this quickly and do some quite complicated stuff. But you'll see this as they progress through this. So to add in some more complexity to the challenge, we want them to add a happy animation when a button is pressed. So quite simple, you press the button, it makes the animal happy. How do they represent happiness through the animation? So they have to think about that. And there are lots of ways to do that. It might just be the animal jumps around. It might be that it has a smiley face. There's lots of ways to do this, and that's kind of really open-ended, and let the students kind of express themselves through that. And then similarly, using a slightly different feature or slightly different input, we want them to create a different animation when the animal is shaken. So get them to think about how an animal would be. How would it react to being shaken? Would it be happy? Would it be sad? Obviously the direction of travel here is that the animal wouldn't like being shaken, and so as you've got the button press making it happy, shaking it would make it sad or angry or whatever. And so we need to think about how would we represent that through animation. And the last one there is how do you add in appropriate sounds. So again, they can apply that however they see fit. So it's a relatively simple set of problems there, but they have to start simply and then add in some additional complexity to make that work. So as before, let's jump into the IPO table and see how we can represent this from a sort of programmatic or systematic angle. And again, you don't need to do this with the learners on paper or on the board, but it's a useful way to look at this. So first of all, with animation, you can have the sort of the default state of the pet. So there isn't really an input, but it just shows the animation. So let's say there'll be 2 frames, and it will show the icon, it will pause, it will show the second icon, and that will loop forever. And it will again show that on the screen. So that is a sort of very, very basic animation, and we'll see a solution to this in just a second. And then building on that, you then want to make the animal happy. So there's a button press, it may play a sound, and then it shows a different animation. And that's important that we have these functions separate. And this is sort of the event-driven element from the computing world, where it does something different when you press the button. And in this case, it's play the sound and play a different animation. And then similarly, again, when the input of shaking is sensed, it then again plays a different animation and plays a different sound. So all relatively straightforward, just incremental steps, incremental complexity, and how we make this artifact work and meet the requirements of this success criteria. So now let's have a look at the solution so we can dig into this, and hopefully this will make it come alive a little bit more. So here we can see the example solution. So the default state is that bit in the middle, so the forever block. So you can see there we've got let's call it a dog. So the first frame there, it shows you the dog facing to the left. It then pauses for 200 milliseconds, and then the head turns the other way. So the dog, as you can imagine, that looping forever. The dog's kind of like looking left, looking right, and that's the sort of the default state for the animal. So that meets the first success criteria, and that's a very, very simple implementation. You could have the dog doing all sorts of different things. It may have different, it could do almost anything. And this is where the students can be really creative. This only uses 2 frames in the animation, but you could have hundreds if you wanted to. Next is the how do you make it happy? So when you're pressing a button, so we've got the on button A pressed there on the left hand side, and that first of all triggers some noise. So it plays the nyan thing once, and then you can see from the animation, whilst that looks similar to the initial or the first frame is exactly the same really as the default state. The pause between it is half as long, so it's only 100 milliseconds, so a tenth of a second. And then the second frame is the image moved up, so it's like it's jumping, and you can see there that the tail there is lifted as well, so it's sort of jumping up and down quite rapidly. So it's it's happy, and you can imagine how a small dog jumping up and down represents the happiness of the animal. So this is where the abstract nature of representing animals through pixels comes into play. So there's lots of different ways to apply that, and students will be very, very creative when they do. The next stage is then is the shaking element of it. And again, you could represent that using the similar iconography that you've designed there, or you could have something more direct. And you can see here we've got some pre-made icons that we use. So it plays a different sound, and it's the melody there is called baddie, which is like a sort of a minor key. It's like a sad sound, and then it shows the sort of the sad face, pauses for a second, then shows another sad face. So the animal's clearly not happy there. So again, lots and lots of different ways to represent these emotions or states using the inputs and processes and outputs. And as before, we have to have that setting the speaker to on at the top as well to make sure that the speaker works on the V2 microbit. So hopefully that makes sense. And whilst these blocks are relatively simple, you can see there's a lot going on under the hood, and students can take this sort of these beginnings and go mad with them. Really, they can add as much complexity as they want to. They could stack in those pauses and those show LED blocks to create really complicated animations. Obviously, you're limited by the 5x5 matrix in what you can do, but there is still an awful lot that you can do with that, and you can create some really sophisticated stuff if they have time to play with it. So hopefully that's builds upon the previous project, and you've got a good example of how you can eke out some of this creativity from this play-based approach by having a good mix of open success criteria, but whilst structured so that they have to apply some of these computational techniques that we've been talking about previously. So next example project. So this is a slightly different one. This has got more of a practical application in the classroom, but hopefully this will be something that is easily applicable. So we're going to create a classroom noise meter. So this is a tool that's going to be used by the teacher. So the context here is your teacher has asked you to create a digital noise meter to let them know when the class is being too loud. So this is quite generic, but you could add in something like the teacher is hard of hearing, and so they don't know when the students are getting too loud, or maybe this could be used when the teacher's out of the room or something like that. So there's lots that you can play around with that context, but really we need to think about how do we use the inputs, processes and outputs to detect the threshold of loudness, and what do we do with that. And again, this project is resource-wise is very, very simple. We can do this with just a microbit. We don't even really need the battery pack for this one, but you can do. And the success criteria then relatively straightforward, but it uses a couple of different or it requires a couple of different features of the microbit programming interface. But they need to design and create a device that measures the noise level and shows it on a chart. So this is where the complexity comes in, because they may not have done charts before, and so you may need to do some prep for this and explain to them what a chart is, X and Y coordinates and bar charts and whatnot. This may form part of a maths lesson or a computer science or an IT lesson. So they have to understand what a chart is first of all in order to be able to understand this. Or you could just let them loose with it and see what they come up with. Or you could even give them part of the partial solution so that it meets the initial success criteria, and then let them play around with the second bit. So it could be a nice short project. So that's the first bit, is getting them to chart the noise level in the classroom. And we'll look at how to do that in just a minute. They also have to have the device to play an alarm sound when things get too loud. So this is the open-ended nature of it. So the students have to determine what is too loud. And I could imagine if this was in the classroom, you'd have lots of fun in you could show the noise level detected by the microbit as represented as a number. And then you can get the class to make lots of noise, and then you could then collectively decide what number is too loud, and then that could be the threshold that you set in the groups, and then you can use that to determine when the alarm is triggered. And then you'd have fun testing that as well, obviously, because the students like making noise, and it's a bit a fun play element to add into this. So whilst the project might seem a little bit dull on the surface, how you apply this and how you deliver it can be quite engaging and quite fun. And in terms of the subject focus, there is an element of physics, so they have to understand what noise is and how the microbit can sense this noise. Maybe you can even talk about decibels and what's the sort of the formal measure of sound. You could even go into the electronics of how a microphone picks up the sound, and it determines the power or the decibel level, but that may be a little bit too far for younger learners. And then there's the computing element of it as well, about how do you set the threshold of noise, and then how you apply event-driven programming to set the alarm off when it reaches that level, which involves a little bit of selection and a little bit of logic, which we'll look at in just a minute. So that's a different take on all of this, and it's something with a bit more of a practical approach and adding a little bit of structure and trying to eke out some of the complexity of the features of the microbit. So let's have a look at the IPO. So the RPO for this one is pretty straightforward. There is a microphone, and it is obviously listening constantly when you tell it to do so, and it's comparing the input to a given threshold, and then when that threshold is met, it will play the alarm tone, and it will, whilst it's measuring that, it will display the noise level on a chart on the microbit. And it's a relatively straightforward chart. Obviously, it uses that 5x5 matrix, so it's not a particularly sophisticated chart, but you can see the peaks and troughs of when there is noise and when there isn't noise, and there's obviously an ambient level of noise, so you'll have to see that all the time. And you can use this, you can see this quite nicely on the microbit when you plug it in and add the code blocks to it. So let's have a look at the solution, because this is slightly more involved than the previous project. So this is about as complicated as we get with these projects, but so it's relatively straightforward, but it does involve some slightly more complex blocks. So let's start on the right. We're obviously setting the speaker to on, as we have done in the previous project, and on the right is where we need to look at this in a little bit more detail. So inside that blue forever block, the first sub block is this plot bar graph of sound level. So sound level, you can see there is that sort of purpley pink. And that is a built-in block which takes the input from the microphone and it plots it, and you can see that up to 255. So the maximum, well, there are 255 points of measurement, and you can set it to be within a particular band of that. But if you put 255, it measures the full range of sounds available on the microbit. So, and if you just have that on its own inside a forever block, it will draw this nice bar graph of sound, and you can test that by clapping near the microbit or shouting at it or getting the class, rousing them to make some noise, so you can see these bar graphs going up and down. And you can have another level of detail if you go into the MakeCode simulator, and you can click on the data tab, and you can see a more in-depth view of that graph going up and down. It gives you a little bit more data, but on the microbit, obviously, it's limited by that 5x5 matrix. Then underneath that, we have some selection. So we are using an if statement, and inside that we have some logic. So this is worth unpicking and spending a little bit of time looking at, because students may not initially know where this stuff is and what this stuff means. So if, I mean, you can explain them, it's testing for a certain condition. So if the sound level is greater than or equal to 200, so obviously the maximum is 255, so 200 is kind of, 3/4 of the way up or whatever, and it's testing when it goes above that threshold, then it triggers the bit underneath it. So it's really important that they at least are a little bit familiar with less than, greater than, and less than and greater than or equal to. So there's the symbols there in the middle. And so if the sound level is equal to or greater than 200, then and only then will it run the next block. And the next block is a loop. And this is, again, another really, really important computational construct. Selection with the if statement is one, and iteration and looping is another. And you can see that in the green block there. So it repeats what's inside that block 2 times. So when the threshold is met, it will loop through that 2 times, and that is plays the middle C, so plays that beep. It plays it once, then it pauses for 100 milliseconds, and then it repeats it 2 times. So that's your alarm. It's the beep, beep, and you can set that to be as many times as you want to. But that is essentially how you recreate that alarm sound when that threshold is met. So that's the sort of the logic of that, and it looks relatively straightforward, but it's worth letting the students explore to see if they can work that out, or maybe you would give them a partial solution using something like the Microbit Classroom, where you might give them that forever plot and if selection, but let them work out where to put the greater than, what the threshold is, and where the sound level bit is, because they could work that out from the bit above it where the sound level variable is in there. So it's you can give them or take away different elements of this to structure this, depending on how long you want to spend on the computational element, or you could just take one bit out and let them work it out. So there's lots you can do with this to focus on the computational thinking elements or not. But this is probably the most complex one I do with younger learners. So hopefully that makes sense, and hopefully you can see how you could do some interesting stuff with these types of projects. So there's some examples of the projects that you can do. using a microbit. Now, when you're coming up with your own projects, it's worth thinking about how to contextualize these in a way which is relevant and engaging, as I've mentioned before, and why contexts are important in the previous session. But a really good source of projects is the global goals. The Microbit Foundation have their own set of projects based upon the global goals, so it's worth checking out their resources as well. But if you just go on the Global Goals website, there are lots and lots of different contexts there, and you can see some of them there, and you can craft problems and play-based activities based upon those, and it's a goldmine of things to play with. So that's a really good source for them to look at, and it makes it relevant and engaging. There's also the Do Your Bit competition from Microbit that they run every year, where students have to come up with a solution to one of the global goals using a microbit. So that's a really, really fun competition, and I encourage you to encourage your learners to take part in that competition. That's really, really exciting, and they're really applying technology to make a difference to the real world, and that makes it thoroughly engaging, and also where they should enjoy doing it and learn a lot whilst doing it. And this begs the question, and I've had this slide in previous presentations, but why aren't we using this sort of stuff more? I mean, the Microbit Foundation conducted some research a couple of years ago about, and you can see from the statistics here that using physical computing as part of play-based learning and project-based learning is very, very effective. And so it does beg the question, why aren't we doing more of this? And it largely boils down to resources and how this type of pedagogy is different and more complex than traditional didactic teaching and learning, and teachers are time pressured, which I completely understand. I was a teacher for many years, and I understand the pressures at play, but the efficacy and the impact that this pedagogical approach allows is profound and should not be ignored. So please do consider this when thinking about whether to apply this or not in your subject. It's not just in computing. This pedagogical approach can be applied to any subject, and you can see the impacts if you craft suitable and relevant and engaging learning experiences based upon this approach. As a next step, it's worth checking out the ArmScore program resources. So there's some links here that you can click when these are shared after the fact, and there are whole courses and lots and lots of projects to play with. There's also lots and lots of resources on the Microbit website as well. For example, the Do Your Bit competition, and the stuff on the Microbit site is really good for younger learners. So similarly to the projects we've explored today, there's ones on there that are even simpler, and they also have some more complex ones as well. So there's a nice spread from the Microbit resources through to the ArmScore program ones, which are slightly more complex and sophisticated. So there's a whole range of there that you can apply to your learners depending on their age and ability and whichever subject you may be teaching. As I mentioned before, whilst these examples are based on the Microbit, there are other boards available. There's a whole swathe of technology out there. Here are the most common ones. You obviously have the Raspberry Pi, which is a full-blown computer, and you can do some really complicated stuff with it. Similarly, you've got the Raspberry Pi Pico, which is a slightly more simple device, but can be used for all sorts of interesting IoT projects and for programming. You've also got the Arduinos and various flavors of that. And it really is for you to decide, have you got these already available? If you're buying them in, what the cost of these are, because they all vary in price. What features do they have, and what's right for your learners. And so obviously you need to make that decision yourselves based upon your resources available. And if you're not familiar with any of these, then I would advocate to start with the Microbit, because it's very, very accessible. It does an awful lot, and you can do some really interesting projects with it. But you can do all of these projects with all of these boards with the right hardware and software interfaces. But that's obviously more for your design and technology and computing teachers to experiment with if they've got the time to do so. So the next step is over to you. We've given some examples of these projects which you are free to use in your classroom and to have a play with, and there is all the ArmScore program resources which you can take and use, and go and design your own as well. Maybe start with some of the ideas we've looked at today, deliver them in your classroom and iterate on them, improve on them, apply these play and project-based learning principles yourself. What I found with these projects is I would initially write them, I would then test it with the class, I would then tweak and change them, and usually by the third time you've delivered it, it's perfect, and then you can use it as much as you like. But do share these online. We really like to encourage collaboration between teaching colleagues as well. Stick them online if there is a place for you to do so. There's lots of communities of practice where you can share these sorts of things. Sharing is caring, and it's a really good idea to put these out there so other people can improve their practice based upon your experience and your learning and delivery. So yeah, please do that, and have a go at creating your own and sharing them online as well. We love to see this as being a sort of the starting point of your exploration in physical computing and project and play-based learning. So yes, do let us know if you come across something useful. And if you do want to learn more about physical computing and all of the elements of it, we've touched upon obviously the simpler end of the spectrum today, but if you're interested in the pedagogical approaches, how to assess it, and some more of the detail around the theory that underpins all of this, there is a course on edX which you can access for free. You just need to go to edX.org and search for project-based learning, and there are 4 courses there that you can use, and these are teacher training courses which are freely available. There is a charge for the certification for these courses, but the accessing the content is absolutely free, so feel free to engage with those resources. And thank you very much for listening to this session today, and I encourage you, if you're interested in this sort of stuff and you've missed the other CBC videos, to check out their YouTube channel and to see the other sessions, and also check out the ones which are coming up in the coming months. So thank you very much for listening to this, and we'll move on to the next part of the session.
Okay, thank you, Rob. Okay, before we go on to Q&A, I'll just hand over in a moment to Surya, my colleague, who'll talk about the feedback form for this session. I hope everyone found that useful. I understand from the Q&A that some people have had bandwidth issues with clarity of the slides and audio, but I hope that came through in the end for you. We've had a few questions through, which we'll cover in the Q&A, but first I'll just hand over to my colleague Surya, who'd like to talk about gathering your feedback on this session. Surya.
Thank you, Nick. Good evening, everyone. I have shared the feedback form link in the chat box.
Okay, thanks, Surya. So if you would like to complete that feedback form, that would be fantastic. You can see that in the chat box. It will take about maybe 30 seconds to complete, and we always welcome your feedback and make sure that we look at it in detail after each session. Right, a few questions that came up. A question came up about the previous session, so I'll just go back to that briefly in a moment. Also about PowerPoints for this session. So after this session is complete, within a few days, we'll be sending you a link to your certificate. So that's how you'll get it, is via email, by the email with which you registered for this session. And you will also be sent the presentation. So that includes the recording of this session. So if you're looking back as you were going through, you were looking back at previous slides and wanting to access them, you'll be able to do that shortly once you receive the that email. Also, there was a question about practical examples of this in action. So I'd really encourage you to, if you're interested in this approach to teaching and learning, whether it's play-based or project-based learning, to go to school.alm.com, where you can access all of our resources free of charge. And there's lots of examples of projects that you can run with your students. That includes project books that you can download for free. There's one here, which is very popular, called Microcourse, and this is really builds on the ideas that Rob presented in the main session, taking you from an introduction to physical computing all the way to block-based coding and your first steps in coding with MicroPython. So let's just go back to the perhaps to the previous slide where we talked about the training that we've done so far and the ones that are coming up. So you can access links to the recordings of all the previous sessions on the ARM Community. So this is the site that you went to register for this session. If you scroll down, you'll see there are links to play the previous sessions. And those sessions really introduce the idea of physical computing, what it is, and the practice of project-based learning in the classroom. The first session is very much starting from assuming no prior knowledge at all. That's get started with physical computing. The second session looks at more deeply at the pedagogical aspects of project-based learning. It looks at the theory that underpins it and how that translates into the sort of practice that we and our partners advocate for in terms of evidence-based practice within the classroom. And then the third session, which is the one that we ran in November, Contexts are Key, really is focused on enabling you as educators to develop your own projects based on contexts that you feel are of most interest to your students. So looking at your cohort, what are the sort of contexts that would really engage them and really motivate them to progress through a project either as a team or independently with you as a facilitator. So yes, please do explore those and watch them if you haven't joined the previous sessions. I should mention as well that there, as we understand it, there'll be no circular for the future sessions. So please do put these in your calendar if they're not already there. So 22nd of February, same time, everyone starts at the same time, 3 p.m. 22nd of February, 15th of March, and 26th of April. There are descriptions of those future sessions on the community site. Surya, we've got a comment here saying the link to the form isn't working. So I'm assuming that this is this may be an issue that is not affecting everyone. But if you could possibly look into that, that would be great.
Yeah, we are receiving responses, so it's working fine.
Okay, good, great. Okay, so just a few other questions that came up from a teaching and learning perspective. There was a question there about PRIM. So evidently someone was very much paying attention at the beginning of the session there, where Rob briefly mentioned the PRIM methodology. And this is an approach to planning programming lessons and activities in the classroom. PRIM is P-R-I-M-M, and it is that's an acronym which stands for predict. So you give students a piece of code. You encourage them to predict what it will do. They take a look at it. What do they think it will do? They then run it to see what it does in practice. Were they right? Are there any surprises there, and why? Investigate it. So they really look at the structure of the code to see if they can understand why it's been structured the way it is. They then start to modify it, so changing perhaps variables within the code to see the effect that has on the output. And then finally, make, where students are introduced to a new problem where the solution is going to require a variation of that code that they've been introduced to. So that's getting them to understand its application and how they can adapt it for new problems. And that methodology was developed by Sue Sentence, actually also based here in Cambridge. She now runs the Computer Science Education Research Centre, which is a joint initiative between the Raspberry Pi Foundation and Cambridge University here. Okay, so another question that came up was around the difference between play-based and project-based learning. So I think for those of you who've joined previous sessions, I think you'll see a lot of the commonalities there between play-based learning and the project-based learning, which we discussed in particular in the first two sessions, looking at the structure and the kind of the way that you can structure the learning and facilitate that as an educator. And I think essentially what the presentation was trying to put forward is that there are you're basically using the same set of tools between play-based learning and project-based learning. The difference is typically the age of the learners and also the level of formalization that's involved in applying those tools and techniques with your class. So just as an example, partway through the presentation, Rob showed the design thinking sheet, which encourages students to plan and sketch their designs for a solution. So in that instance, you adapting it for younger learners, you might really focus that planning session on sketches of their ideas, as opposed to the more formal parts of that. So a lot of commonalities there, which is why it forms part of this series of webinars that focuses on project-based learning. And another question about the application of this to other subject areas. So Rob did mention that the approach, play-based learning approach, project-based learning approach, can work with other subject areas. And I think hopefully that will have come across in the presentation. You can see a lot of opportunities there for extending it into other subject areas and also working across the curriculum, whether it's at primary school or into secondary school. As an example, the Animated Animals project, that could form part of a wider investigation into the natural world, which could bring in science, it could bring in literacy. You could perhaps extend that to look at how technology is being used to protect the environment by monitoring, using sensors to monitor things like migration patterns. For more advanced students, you might look at how the kind of sensors that would appear in the physical computing devices that we're talking about, microbits, Arduinos, etc., how they are being used to help stop deforestation. So there is sensors are being used to capture the sounds of forests, and AI is then used to identify within those sounds the sound of chainsaws, which enables conservationists to understand where logging is happening and target that and hopefully reduce it. So there's a lot of opportunities for extending this kind of approach into other subject areas. And then a final question that's come up, I think, is a very practical one about where I can buy physical computing kit and how much does it cost. Well, I think it's important to say that, again, as I covered at the beginning of this session, that ARM doesn't manufacture or distribute the sort of physical computing devices that we've been talking about in this series. It's really that our technology underlies the microprocessors that appear within them. But you can find, I think, if you put it in a search engine, if you search for the device, you can find links to local distributors. As an example, I think the Microbit V2 Go kit, which gives you everything you need to get started, it includes batteries, is in the region of 1,400 rupees, just to give you an idea of the cost of that. Okay, so let me move on to the final bit, which is really to say thank you for joining us today. Really appreciate your taking the time out to join these sessions with us. I would like to thank once again CBSE, Dr. Saha and Mr. R.P. Singh for the opportunity to collaborate on these this series of webinars. In terms of next steps, we've talked about the edX program that we have available. If you're interested in any of the themes that we've discussed today or any of the other webinars, please do search for Teaching with Physical Computing on edX.org sign up for free, and you can take a deep dive into these topic areas. The feedback form is in the chat. We'd very much welcome those your feedback if you can provide that to us. And we hope to see you at the next session in February. Okay, we'll close it there. Thanks very much. We'll see you next time.